In the previous lecture we started talking about frames, and I introduce you to some examples of frame problems, and we also try to solve one problem within the topic, and this was that problem. So in this lecture I will solve one more problem in frames, and then we have to move on. So let's say we have such a structure for which the question here is in each case identify any two force members and then draw the free body diagrams of each members of the frame. Find horizontal and vertical components of support reactions from A and C. So that is the question here. And like I've told you before, this is not a truss. You can see that for example in member AB, at the middle of the member AB there is a pulley on which there is a tight rope, at the end of which 200 Newton force is being applied. The radius of the pulley is given. So because of this force by the rope on the pulley, there is going to be an external force on AB. I mean, if you are considering AB alone, there will be an external force on it by the pulley, so which is not a force on the joint. So that makes this a frame and not a truss. Now let's go ahead and see how we can solve this problem here. So our target here is to find the horizontal and vertical components of the support reactions from A and C. So I'll take enough time, and we will not be in a hurry to solve the problem. I'll just we'll go slow and easy. So this is not very difficult. You have two linear members AB and BC, and this is a pin joint here, and pin joint here. So for member BC seems to be a simple member because there is no force on the member other than the joints. There is no moment on it, so that means that in BC the external force will be in the direction of the bar. So if we try to draw free body diagrams, let's just draw AB first there and BC here. Okay, so this is AB and this is BC. So at AB, at the middle of AB, there is a pulley, and if I draw the pulley separately, let's say that's our pulley, and there is a rope on the pulley, and a force Newton is being applied on the rope. So if this is the case, this angle here, this 200 Newton force is vertically downwards, which means that so this is we have to assume that this pulley is frictionless, since it's not mentioned otherwise. If the pulley is frictionless, the force on the pulley should be same everywhere. So 200 Newton here and 200 Newton here. So what does that mean for us? So this pulley must be in equilibrium. What are the different types of external forces on the pulley? The rope which is wound on the pulley has 200 Newton force tension on it. So 200 Newton, one here and one here. And what will be the other force on the pulley? There will be a force from AB on pulley, right? Because the pulley is fixed on AB. So what will be the direction of that force? What will be the direction of the force? What will be the magnitude of the force? That is quite easy here, because this each of the member AB, BC and pulley should be in equilibrium separately. So that means that force by the bar on the pulley should make sure that the net force on pulley is 0. So net force in x direction should be 0, net force in y direction should be 0. So you can choose any arbitrary direction for the third force, and you can calculate the direction and magnitude from the fact that the pulley is in equilibrium. So if the pulley is in equilibrium, what this angle here this is actually, if you have the right intuition, it's very easy for you, because this force is 200 Newton here and 200 Newton here, and some of that force will have a direction which makes 45 degrees the horizontal. So to cancel out that force, there should be another force, external force in this direction, and that should make 45 degrees the horizontal. The magnitude will be the sum of the vector sum of 200 and 200. But if you like to do it procedurally, you can do that. You can calculate this theta and this magnitude using the standard procedures. But I would anyway, the fact that this is 45 is quite obvious from here, because this is both 200. This is 200 and this is 200, and the resultant of the force must make 45 degree with the horizontal. So if this is 45 degree, the resultant here, which we call R, now the net force in x direction should be 0, net force in y direction should be 0. So that means that net force in x direction 0 means 200 is equal to R cos 45, and R is equal to 200 divided by cos 45, which is 1 divided by root 2. So this is the magnitude of R. So if the force by AB on pulley is R, the force by pulley on the bar should be in opposite direction. That's the Newton's pair, and it should have the same magnitude, direction opposite, and this angle should be 45 degree, and the magnitude here is R, which we have already calculated, which is 200 root 2. Now what will be the other external forces here? So there are reaction forces, for which we can assume the direction. Let's assume that there are so the reaction from A in x direction should I type it? We'll call it R A Y. Okay. This is R A Y, and this one here is R A X. Okay. Now here similarly there will be reaction forces at B also. For which you can assume the reaction from B in y direction, and reaction at B in x direction. Now these are the unknowns for member AB. How many unknowns do we have here? 1, 2, 3, 4. 4 unknowns, but how many equations do we have here? We have only 3 equations. Which are the 3 equations? Net force in x direction is 0, net force in y direction is 0, net moment about any point is 0. So 3 equations and 4 unknowns, so you can't solve it here, you need help. Now for BC is an interesting case. There is no there are no moments on BC and there are no force within BC. So this basically acts like a truss member. So if it acts like a truss member, the direction of the force can only be in the direction of BC. But however, since we are taking RBY and RBX component here, let's draw the same thing here. That will be easier for us. So the force by BC on AB in vertical direction is RBY. So the Newton pair component should have the opposite direction. I will explain this in a minute. So this is magnitude will be RBY and RBX, right? RBX here. So this RBX here is the force by BC on AB. Its direction is this towards right, and this is the Newton's law pair, which means the force by AB on BC. So it will have the same magnitude but opposite in direction. RBY here is the force by BC on AB. Its direction is upwards, and here this force is the force by AB on BC. So its direction will be opposite but same magnitude. That's what we know about the Newton's law pairs. And now here similarly you will have forces here also. So this is basically reaction force at C in y direction, and here you have force, reaction force at C in x direction, and we have assumed these directions, and I think it's pretty safe to assume that because these are opposite, or you can't assume it otherwise also, it won't create any problem. So now it seems we have two systems here, AB and BC, and how many unknowns in total? 1, 2, 3, 4, 5. No, RBX and RBX are same. So I'll just write down the unknowns. I think it's easier that way. So unknowns are AY, AX, BY, BX, CY, CX. So how many unknowns do we have here? 1, 2, 3, 4, 5, 6 unknowns. How many equations do we have? 3 equations here, 3 equations here. Net force in x direction 0, net force in y direction 0, net moment 0. So 3 equations here, 3 equations here, 3 plus 3, 3 equations and 6 unknowns. 6 equations, 6 unknowns. So the system is closed and you can very easily solve the problem. So if you want me to write down these things, I can do that. So we have so it won't go fine. Now net for this particular system, equations are net force in x direction 0, that means that RAX minus RAX is in leftward direction, plus RBX, that is towards right, minus 200 root 2 cos 45, 200 root 2 cos 45 components is there towards left, so sum should be 0. Net force in y direction should be 0, so that means that RAY acting upwards, RBY acting upwards positive, and minus 200 root 2 cos 45 or sin 45, both are same, is acting downwards, so sum should be 0. So these are the 2 equations, and you can write down a third equation if you like. So yeah, third equation you can write about any point A, B, whatever you like. I think it will be interesting to write down the equation about this point here, so that or about A, B, or this point, anyone will do. Okay, I'll choose A. Net moment about A. So you have to consider all forces. RAX multiplied by the perpendicular distance between line of action of RAX and point A, that is 0, so RAX multiplied by 0, gone. RAY, the perpendicular distance between line of action of RAY and the point A is 0, RAY multiplied by 0, gone. 200 root 2 has 2 components, 200 root 2 cos 45 in horizontal direction and 200 root 2 cos 45 in vertical direction. So 200 root 2 cos 45 in horizontal direction is passing through A. That means that perpendicular distance between line of action of this horizontal force and the point A is 0, so that multiplied by 0, gone. But it has a vertical component, 200 root 2 cos 45 vertical component, for which, so this will be the vertical component. So the line of action of the vertical component of the force and the point A is if I remember correctly, that is 2, so this multiplied by 2, and this is causing a clockwise moment. So about A, this is causing a clockwise moment, so that is let's take it as negative. And then let's consider RBX. What is the perpendicular distance between line of action of RBX and point A? This is the line of action of RBX. So the line of action of RBX is actually passing through A. So the perpendicular distance between line of action of RBX and the point A is 0. So RBX multiplied by 0 gone. And you have RBY. RBY, the perpendicular distance between line of action of RBY and the point A is 4, and it is causing an anti-clockwise moment about A, so let's take it positive. So these are the forces we need to consider here, that is equal to 0. So from this equation you can calculate RBY, and RBY can be substituted here to calculate RAY, and now RAX and RBX are remaining, for which we need to take out the next set of equations. So for that let us take this part here. It's not good enough. Yeah, that's good enough. So for this member, net force in x direction is 0. That means that minus RBX, this is minus because it's acting towards left, plus RCX is equal to 0. That means that RBX is equal to RCX. Net force in y direction is equal to 0. That means that minus RBY, because it is downward direction, plus RCY is equal to 0. It's plus because it's acting upward direction, so RBY is equal to RCY. So RBX is equal to RCX and RBY is equal to RCY. RBX, CX, CY. Okay. So we have enough equations here. Yeah, and also moment equation can also be written here, because since we do not consider the direction, it's important for us to write down the moment equation also. Moment about which point can you write? Any point. Let's take moment about B is equal to 0. So the moment equation, okay, I'm writing it down here. So the net moment about B, the RBX and RBY are passing through B, so the lines of actions of those forces passes through B, so those forces will get multiplied by 0 and those terms will disappear. So we don't need to consider RBX and RBY, but RCX this is the line of action of RCX and this is the line of action of RCY. And these distances should be marked. This distance is 1.5. This distance here is 1.5. And this distance is 2 meter, this distance is 2 meter. Now in the moment equation, this and this are gone. Now RCY multiplied by what is the perpendicular distance between line of action of RCY and point B. This is the line of action of RCY. So the perpendicular distance between line of action of RCY and the point B is 1.5, and about B it is causing an anti-clockwise moment. You can see that this is the direction of force, so this is causing an anti-clockwise moment, hence it is positive. And RCY, this is the line of action of RCX, and it is causing, this is the direction of force, this is the direction of force, so it's causing an clockwise moment, so it's negative. So RCX multiplied by 2 is equal to 0. Now you have enough equations. So this seems that it's making things quite easy here. It's RBX is equal to RCX, RBY is equal to RCY, and RCY and RCX has this relationship. So that along with okay, where is the other equations? Okay, that along with this set of equations, you can very easily solve the problem. So I think that last steps I will leave it to you, but I have made significant progress. You just need to RBY we have already calculated, RAY we have already calculated. So the only thing remaining here is RAY and RBX, and that can be used along with this and this equation. You will get the solution very easily. So with that we will conclude the frame section here, and in a new lecture we will start the next module. I know that there are more topics left here in this module. We will just come back to that. Before that we will start talking about moment of inertia, area moment of inertia, the first and second moment of areas, etc. So I shall conclude it here.